So we are talking about resistors in series and parallel. We're looking at resistor circuits, and we did a couple of examples last time. So last time we applied the loop law and the junction rule to a couple different circuits, and then I introduced you guys a series and parallel circuit. I want to do one more example with that, because the more examples we have, the better we become at it. So I want to do one more example with a series and parallel circuit, analyze that, and then once we do that, we're going to look at a couple other topics, namely power, because we haven't looked at power yet, and RC circuits. Okay, so that's what I want to do today, and that should wrap up chapter 28 in the 4th edition, and will set us up for our next lecture, looking at chapter 29. And this is, by the way, this is the last chapter that we deal, that's particularly pertaining to DC circuits. Then we're going to take a break from electric field and circuitry, and we go into magnetic field. So that's kind of the next big topic that we're going to be looking at in chapter 29 and chapter 30. Okay, so let's wrap up chapter 28 now, and then we'll in the next lecture we'll jump into magnetic fields. So looking at resistors in series and in parallel, and we know a couple characteristics about these. So for series, this is what we saw. Resistors always have the same current. Okay, and their voltages, you add their voltages. So voltages are summed. Okay, so draw a quick, let me put that in a different color. Draw a quick picture about that, just by way of reviewing here. Okay, so something like that would look like you have your battery and resistor. Okay, so this will be how it looks like when you have resistors in series, right? And we said that the current will be going this way. Okay, and if there's no junction, the current stays the same. So the current going through here is the same current going through there. Right, so that's why I said there, resistors in series always have the same currents, and their voltages are going to add up. Okay, so you have your voltage across R1. Put that in a different color. So I'll call that V1, and voltage across resistor 2, and you could add them up, V1 plus V2. And in this case, since they're the only resistors in the circuit, that's going to equal your voltage of your battery. Okay, which again, that would come from the loop law, right? As you go in a loop around this circuit, your total voltage should be 0. Okay, so that's resistors in series and in parallel. Let's talk about resistors in series. Let's talk about resistors in parallel. Again, I'm just reviewing here, because we're going to use these concepts in the next example. Okay, so resistors in parallel, resistors have the same voltage. Okay, when we have resistors in parallel, but different currents. Let me say, but can have different currents. Like if you have two resistors that have the same resistance, they're going to have the same current as well, but that's kind of the exception. All right, so the circuit for that will look something like this. You have your battery, and for resistors in parallel, it splits up, right? So you have a junction there, and it splits up into two resistors, right? So here is my junction. I'll put it in green. I have a junction here and a junction here. Okay, so at those junctions, you have the currents splitting. Okay, so you have current going in like this. Oh, wrong. Let's see. Okay. So you have this is the current from the battery. Current from the battery splits up this way here, I1, and goes down this way, I2. Okay. All right. So current splits up. So the currents equal the sum of the currents equal each other. So I1 plus I2. But I can't say the voltages are the same, right? And I explained this last time that the voltage along this whole wire here, all that voltage stays the same, and the voltage on the bottom, voltage in those bottom wires stay the same. So each resistor has the same voltage difference. So I say voltage of V1, voltage V2, right? The voltage of those two resistors are the same. Okay, so those are the key characteristics of the series and parallel, and of course we have our equations for equivalent resistance that we derived last time. So R equivalent equals R1 plus R2, and etc. if you have more resistors in series, and then R equivalent for parallel is 1 over R1 plus 1 over R2. So yeah, this is supposed to say currents. Cool. All right, so key characteristics that we talked about last time. Like I said last time, it's the equations on the bottom, right, are important. We do use them, but if you can't recognize the characteristics within a problem, right, what I wrote on the top there, then doing the problems are going to become difficult. You kind of need both, right? You need to know the characteristics, and you need to know their equations. Okay, so that being said, let's look at a circuit. And I want to analyze the circuit and see what we could find from it. Okay, so it's kind of your typical problem. So you're going to be given a circuit, and for that circuit, we want to know what's going on with all these resistors, right? What's the current going through each resistor, and what is the voltage going through each resistor? So let me give you the how the circuit looks like. Okay, so start off with the battery, and I have current coming from the battery. Oh, nuts! I meant to put another resistor. Let's see what happens if I erase this. Yeah, I thought so. There you go. Okay, so here is my resistors. Let's say this is a 10-volt battery. 10-volt battery there. I have, I'll call this resistor 1 equals, let's do 15 ohms. Resistor 2, 10 ohms. Resistor 3. Let's see, that's 15, that's 10. We'll do 20. And resistor 4, we do 5. So there's my resistors. And oh, this is supposed to be resistor 1. Doesn't really look good. Okay. Okay, so there's my resistors, and so again, I want to find out this. I want to answer this question. So what I'm going to do is essentially fill up this table. So I'm going to make a little table here. It's probably too long, but I have R1, R2, R3. You know what? I'm going to run out of space really quick doing it that way. Okay, and then we're going to find the voltage. I don't know why am I writing so bad today. Voltage and the current for each one. Okay, so I want to essentially fill up this table. For each R1, R2, R3, R4, I want to find the voltage and current for each one. All right, so the way we start off with this, so I don't know anything about the current. So a good place to start is to figure out how much current is coming from the battery. Now we know that current, at this junction right here, that current is going to split off. I'll call this I1 here, and I'll call this one I3, just because it goes towards resistor 3. Okay, so I know that current's going to split off. There's no I2, don't get tripped up that I didn't write I2. I just call it I1 because it goes towards resistor 1, I3 because it goes towards resistor 3. Okay, so it would be helpful if I knew what that current was. Okay, and so what we're going to do with this, and it's kind of standard, is to simplify this to one resistor, right? I want to get the equivalent resistor for this whole circuit. So in doing that, we've got to look at what's happening as far as which resistors are in series and which resistors are in parallel. This is the hardest part, and I think with practice, everything else you guys get good at as far as doing the calculations, using Ohm's law. Usually when I look at your work from quizzes and from exams, generally speaking, students are able to do that. The mistake comes in finding which ones are in parallel together and which ones are in series. All right, so if I look at this, let me try to color code it. I hope this will be helpful for you guys. I'm gonna color code it here. So I'm gonna ask myself which wires have the same voltage. So these wires, wrong one. This wire right here, all have the same voltage, right? They're all connected together. And so they'll have a voltage. Now R1, if you look on the right here, R1 is going to give me a certain voltage drop. And R3 is going to give me a different voltage drop, right? They have different resistances there. So, and they're also going to have different currents too. But we're going to assume that they're going to have a different voltage drop here and here. So that means they're going to have different voltages. So I'm going to represent that as different colors. Hopefully I don't run out of colors really quick. Okay, so this is going to be a certain voltage drop, right? We don't know what that voltage drop is. And R3 gives us a different voltage drop than that. So let me pick, I'll pick one. Okay, so then I get a different voltage drop there. Okay, so you could see here that R1 and R3, because of that different voltage drops, we can't say R1 is parallel to R3, right? Remember what we said about things that are in parallel? Go back here. Things that are in parallel have the same voltage, right? Same voltage drop. And you can see it with V1 and V2 in the picture there. So they have to have the same differences in voltage. You look at R1, that goes from blue to green, and R3 goes from blue to orange. So different voltage drops there. So you can't say R3 is parallel to R1. Okay, and let me finish that. I have one more. And then I have voltage drop over here. Okay, so again, all these colors represents different voltages. And what I'm hoping you see there is that R3 is not in parallel with R1, but there is a junction there, right? So if we follow the current, here's the current. The current goes through R1. There's no junction between R1 and R2. If there's no junction between R1 and R2, right, that means that whatever current I have, I1, is the same current through R2. So both of these here have the same current. What does that tell you as far as series or parallel? It should show that these are going to be in series together, okay, because they have the same current flowing through them. Okay, and again, there's no junction here. I mean, you have a corner here, but that corner isn't a junction, right? It's not like the current has an option to flow this way. The current just has one direction to flow. Okay, so R1 and R2 are in series, and I'm going to start with that. There's let me say, maybe you're thinking like, well, can I say the same thing about R3 and R4, right? No, you can't say the same thing about R3 and R4 because you do have a junction between them. The current going through R3 is not the same current going through R4. Okay, you have different currents between these resistors, so they're not in series. Same thing with R2 and R4, right? R2 has a different current flowing through it than R4 does. Okay, so we can't say these two are in series. So let me see here. So I'm going to start off. I'm going to start off with R1 and R2. Okay, so I'm going to focus on those two because those two are in series, and I'm going to combine them. Okay, so let me do that. I'm going to combine those. I'm going to, every time I combine something, I'm going to draw a new circuit diagram here. Okay, so this new resistor on the right is my R12. I've combined resistors 1 and 2. This is still R3 over here, and it's still R4. Okay. So what would that new resistance be? Well, we could find out pretty easily. Resistors in series. Well, we said resistors in series, if we want to combine them, you just add them. So R12 equals R1 plus R2, right? Because they're in series, I'm able to use that equation. And so what do I get there? R1 plus R2 gives me 25. 25 ohms. So that's my R12. All right, so now I'm looking at this diagram here. I have R3, R12, and R4. And again, I'm going to ask a question, which resistors are series and which resistors are parallel? So R3 and R12, if you look at those are definitely in parallel to each other, right? They have the same voltage difference between them. So the next ones I'm going to focus on. Okay, cool. It was helpful. So let me do that then. Okay, so I'll try to keep the same colors I had last time. So this is a voltage here from the top of from the battery. So this is whatever, I guess 10 volts is what it would be, right? So did I say 10 volts or yeah, 10 volts? All right, so all those wires have the same voltage. On the bottom, they're gonna go through, there's R3 and R12, yes, different resistance. All right, they're not necessarily the same resistance, but because they join together again on the bottom, let's see, what color should I do? I'll do orange. That means right here, the voltage here and the voltage here are going to be the same. Okay, so because those wires join together. So we see something that we saw before, right? In the parallel setup, going back here, you have two resistors have the same voltage difference, right? I'm looking at that blue and that pinkish reddish color. So the pink and the red, oh sorry, the blue and the red indicate that V1 and V2 are the same voltage. We get the same thing here, right? You have blue to orange for R3 and blue to orange for R12. So they have the same voltage difference. And we said that if they have the same voltage difference, that is a characteristic of parallel. Okay, and then of course we have that other one on the end here. This right here, which is going to be 0 volts. Okay, so that tells me that these resistors I'm going to be looking at here. Okay, the R3 and the R12 are in parallel, and those are the next resistors that I want to combine. Okay, so let me do that. So I'm going to combine how should I do this? Okay, so this is R, let's call it 312. Okay, so R3 and R12 combined, and on the bottom here, I still have my R4. Okay, So I could combine my R312, or I could find out what R312 is. Okay, R312 equals, and so we know R12 and R3 are in parallel. So for the parallel connection, here's my equation for my resistance. It's 1 over R3 plus 1 over R12 to the -1. Okay, and that's supposed to be a plus there. Okay, so like we have those numbers, right? R3 is 20, R12 is 25. So I didn't bring my calculator out. So let's plug that into a calculator. Let's see here. 1 over R3, which is 20, plus 1 over R12, which is 25. And don't forget, it's very easy, just get your number and forget to take the inverse at the end. Okay, so when I do that, I get 11.1. Point. Okay. All right. So there we go. So as far as now, what do we have left here? Well, I mean, I could do the voltages again. We have the voltage coming from the battery. Oh, wrong one. Voltage coming from the battery. We have the voltage between the two resistors here, and we have the voltage going to the battery. Okay, so we look at that, we definitely see the different voltages there. So even though I drew it like this, right, don't take that to be that these resistors are in parallel, right? They're not in parallel. They don't have the same voltage difference between them. But what is the same between them is that current, right? The current is coming out this way. And there's no junctions here, right? That current doesn't have an option to split off. So what we're looking at here is R312 and the R4 are both in series here. So I'm going to combine it one more time, whoops, into a simple circuit like that. And I'll call this the R4, 3, no, you know what, that's going to get too big. I'm not going to write all those numbers. It's just R equivalent. And this is my 10 volts here. Okay, so what is this R equivalent? Well, look at the previous step. We did R312 and R4 together. So my R equivalent here, if we're doing series, which we are, right? The R312 and the R4 are in series together. R312 plus the R4. So all we're doing is adding those two resistors together. So 11.1 plus the, I think I said 5 ohms resistor. My windows are covering up, so I can't see. So it's 16.1 ohms. Okay, 16.1 ohms there. So that is my equivalent resistance. Okay, now why do I want to find the equivalent resistance? It all goes back to how I started this whole thing. So I said over here, it would be helpful if I knew this I, right, coming from the battery, because then I could eventually figure out what this I1 is and this I3 is. Okay, so I need to know this I. Well, here in this picture, it's really easy to find out what that I is, right? Same I, oops, same I as the picture on top. If I have the voltage and the resistance, right, finding I is just a matter of using Ohm's law. So I, do it a little bit neater. I equals V over R equivalents. In this case, it's going to be 10 volts over 16.1. So just a little tip here. in my calculator, even though I wrote 16.1 in the on the whiteboard here, I'm keeping extra sig figs in my calculator. So it's just to avoid any kind of rounding errors. All right, so I get 0.62. 62. I'll keep one more sig fig. 1 amps. Okay, so that is how much current is coming from the battery. Okay, so going back up here to my first picture, I know this current is 0.621 amps, which means I have the current for one of these resistors. Okay, which resistor do I have the current for? I guess let me be more specific. Going back to my table here, I could put this 0.621 somewhere. Yeah, it's R4. Okay, so what's going to happen with my current here? So my 0.621 comes here, gets split up. We don't know how it gets split up yet. Okay, but it gets split up, goes through these circuits, recombines down here, this junction, and then goes to R4. Well, when it recombines, we get that current that we had earlier back. The 0.621 goes to R4. So I know, let me see here, that my current for R4 is a 0.62 amps. Okay, and if I have my current for my resistance and I have my resistor, right? My resistor right here is 4 or 5, I should say, 5 amps, ohms. So I have 5 ohms for my resistance, 0.62 or 0.621 for my amps. We could find voltage, right, using Ohm's law. Voltage equals IR. So 0.621 times 5, and what we get there is a voltage of 3.1. Okay. So that total current, we had to do all that work to get equivalent resistance. Well, that total current allowed us to find the current and voltage for R4. Okay, it's going to require a little bit more work. It's going to require for the other resistors, but at least for this one, we could get it pretty quickly. All right, so let's look here and what we're going to do is kind of work backwards. We start off with our equivalent resistor, and I'm just going to go to this one here, see what information I could gather from this picture. Then I go here, what information could I gather from this picture? Then I go to my initial picture. So we're going to work backwards here as we kind of analyze the circuits that we drew. Okay, so let's go to this circuit right here. So for this circuit, we know the currents, right? The current is the 0.62, right? 0.621. So this is a current flowing through this one. We already dealt with R4, so we have everything we need for that. So I'm ignoring it now. And let's focus on this one. The R312, I know the current going to this one. And because I know the currents, I could find the voltage, right? So let me write that off to the side. Let's see if hopefully I have enough space here. The voltage for 312 is just going to be the current going through 312 times the resistance of 312. Okay, so we know the current. The current is a 0.62, right? That's what we calculated earlier. The resistance for the R312, what we also calculated that earlier, is right here, 11.1. Oops. So we plug that into our calculators. So 0.621 times that resistance, 11.1, and we get 6.89 volts. Okay. Okay, so that doesn't really tell me anything. Oh, actually, that's really important. Okay, so why did I have to get the voltage here? Well, remember what the R312 represents. The 312 represents these two resistors, right? R3 and R12. And look at, I don't know, for some reason I chose a different color. I was trying to keep the colors coordinated. this color, right, this voltage refers to this voltage here, right? It's the same voltage. And this voltage down here, this orange one, refers to the same voltage down here. All I did was combine these two resistors. So when I calculated a voltage of 8.9 or 6.89, the 6.89 referring to this resistor is the same voltage difference as for the R3 and as for the R12. So in doing this calculation, V312, this voltage applies to both resistors in parallel. Okay, so I have the voltage for R3. Voltage for R3, and I'm going to keep that to 2 sig figs, is 6.9 volts. But essentially the voltage of that R312, because it is representing the voltage of two resistors in parallel, this voltage is going to be the same voltage for both of these. Okay, so now that I have voltage for 6.9 for the R3, I have voltage, I have resistance, right? R3 was my 20 ohms, a 20 ohm resistor. So with voltage and resistance, I could find current. Right, so V divided by R. So voltage, 6.89 volts divided by 20. And I get 0.34. Okay, so I'm on my way, Yes, the R312 and the R4 are in series. But don't get confused with what I just got with the current. The 0.34 that I just calculated is referring to just R3, this current right here. So I just found I3. The R312 and the R4 will not have the same voltage. So because they're in series, series have the same current, not the same voltage. Okay, I hope that answers your question, or that clarifies that confusion. Okay, so yeah, the R312, R4 are in series, but they're going to have the same current there. They're not necessarily going to have the same voltage. Okay, so let's go back here. So I've analyzed this picture here, and I'm going to keep doing what I said. Once I analyze this picture, right, I got my voltage, I got my current. There's really nothing else to find here. I'm going to go up to this one. I don't care about R4 anymore. We found everything for that. I don't care about R3 anymore. We found everything for that. So I'm going to focus on this resistor here. Right, this is what I don't know. Right? I don't know anything about this. I don't know voltage. Well, actually, I do know voltage, and but I don't know current. All right. So as far as voltage goes, remember we found the 6.89. That is the same voltage for both of these. Right. So I do have my voltage. Let me write that up there. I do have my voltage for my 1-2 resistor. So V12 is at 6.89. Okay. So I have my voltage for the 1-2, and I also have current. You could either use Ohm's law right here, right? I equals VR, or V over R. Right, so we could use Ohm's law, or we could just kind of use logic here, or the junction rule. If I have 0.621 amps this way, and I just calculated I3, right? So I3 was 0.34, and I'll put an extra sig fig there. 0.34, what was that, 5? Okay, so my total current is 0.621. That current gets split off 0.345. Well, whatever's left over will be going towards my we call it I1 earlier, would be going to my R12. All right, so I'm just using junction rules. So you could actually figure this current out in two ways. That's what I'm saying. You could figure out using this way, this voltage over this resistance, right? Your total your voltage across 1, 2 divided by your resistance of 1, 2, or, so that will give you that's one way of finding current, or you could see how the current splits up. 0.621 here, 0.345 of it goes this way, and whatever is left over goes down here. So it doesn't really matter which one you choose. You should get the same answer at the end. So if I do that, I get a current of, let's see, 0.276. Okay, 0.276. That's my current going to R12. Which is important, right? Over here. Oh, I wish I could delete it, but I can't. All right. Oh, wait. Let me probably like this. No. Okay. Well, let's leave it there. Okay. So this I1, right, that we calculated 0.276, goes through. We talked about this earlier. They have the same. They don't have the same voltages here. R1 and R2 do not have the same voltages. But what they do have, because they're in series, is the same current. So this current that I calculated, the 0.276, goes through both of these. Okay, so I can fill up my table. I have 0. Well, I guess if we're going to put, two suffix here, 0.28 amps for my R1, and R2 is in series with R1, so that's also going to have the same current. Okay, so pretty much that's it. I have enough now just to do a simple calculation to figure out these voltages. I have my current through R1, I have my resistance through R1, and I could just use Ohm's law, right, to find the voltage. So if this is my current, that's my resistance. All I have to do is current times resistance, and I get 4.1 volts. Let's see here. For my R1. And for R2, well, it'll be a very similar calculation. Just the current 0.276 times my 10 ohms. And that's a 2.6. No, sorry, not 2.6, 2.8. That makes sense. There we go. And I solved this this question. All right, so can you explain again why R1 and R3 are not in parallel? Yes. So R1 and R3, remember so be careful. Just I know it's tempting to look at R1 and R3 and you see that, yes, they are physically parallel to each other. But when we ask, are they parallel in their circuit construction or as far as circuitry goes, we said that parallel, not only do they have to, it may not actually look like this for circuits to be parallel. Just because they're parallel does not mean they're in parallel. What we have to make sure is true is that R1 and R3 have the same voltage drop across them. So this is why I did the colors. So this color here represents a certain voltage. In this case, because it's 10 volts, all this blue is 10 volts. Then the orange here represents a different voltage, and the green represents a different voltage. So R1 and R3 do not have the same voltage drop across them. This one goes from 10 to a value. I'm not sure what value that is. I can do the calculation if you guys want. But it goes from 10 to some value, and R1 goes from 10 to a different value. So they have different voltage drops, and so that's why they are not in parallel. Okay. I will say this too, that if we want to see what's in parallel with R3, you got to ask what goes from blue to orange, right? That would represent the same voltage drop. Well, we have blue over here and orange over here. So blue to orange, that would be the same voltage drop. And so this whole thing here is in parallel with R3. So it would be incorrect to say just R1 is in parallel. It's this whole thing here, R1 and R2, that's going to be in parallel with R3. Okay, how did I get the 0.34 amps? 0.34, where did I get that from? R3. Okay, oh, right here. So the way I got 0.34 amps is, oh, right here. No, where did I get that from? Oh, okay. So if you remember, where did I get the 0.34? I found it through, let's see. So I have this voltage, 6.89. Oh, okay, that's right. So I found the 6.89 volts here, right? This is where hopefully you got where I got, you're able to see where I got this voltage. It's just this current times resistance, right? This resistance here. So my current, which I got earlier, times that R312 gives me this voltage. All right, so that's where I got this voltage here. Well, once you get voltage and you know resistance, right? R3 is 20 ohms. Once you get voltage and resistance, you could just use Ohm's law to find current, right? Voltage divided by resistance. So I took this 6.89, divide that by 20, and that's how I got the 0.34. Okay, great. Yeah, the 0.28 amps. 0.28 amps. Okay, so that's really up here, right? So for that one, I said there's two ways you could calculate it. You could see that I have 0.621 amps. That's the same thing. The same current I calculated down here for the current coming from my battery. So the current coming from the battery is 0.621. It hits this junction, and some of that current goes to the right. Some of that current goes down. The current that went down, we calculated was 0.345 amps. Okay, so 0.621, some of it goes down, 0.345 of it, and then I have to figure out anything left over goes to the right. So, and you can see that if you do 0.276 plus 0.345, should give you 0.621. Okay, so that's where I got the, and then I did, when I put it over here, I did 2 sig figs for my final answer. But it came from this. The other way, okay, go. Let me say the other way to explain, even though you didn't. I'm glad you got it. The other way to do it is by taking this voltage divided by this resistance. So 6.89 divided by your 25 ohms, right? That'll be the voltage from the blue to the orange. That's a 6.89 divided by the resistance here. So that should also give you the 0.28. So either way it gives you the same one. All right, so I think we're gonna take a break now. I was hoping to get through this problem, but yeah, this problem took me a little bit longer than expected. We're gonna take a break now, and we'll come back. We're gonna look at two things: power in circuits, and RC circuits. We're gonna put a capacitor and a resistor together and see what happens then.